All right, let's take a look at some material from lecture 16. This is more stuff about normal distributions. As usual, I gotta say that watching videos is no substitute for reading the book and notes. Book and notes are primary materials. These are supplements. All right, we're going to start with transforming back and forth between x and z. You'll see what that means in a second. So I have some normal curve over here. Oh, it's the normal curve with mean mu and standard deviation sigma. And I think of there being a random variable x which has the corresponding normal distribution. Over here I have the z distribution, the standard normal distribution with mean 0, standard deviation 1. And of course the random variable z always has that distribution. Okay. If I pick a point here over on the x-axis, call this point C. If I pick a point over here, the area to the left of it, well, I don't know what it is, let's call it A. But anyway, it's less than 1. The total area under here is 1, the total area under here is 1, and so there has to be a point on the z-axis so that the area to the left of that point, well, let's call it D over here, the area to the left of D under the standard normal curve is exactly the same as this area A, that is the area to the left of C under this normal curve. So I can color in this area here and label it A. Those two areas have to be the same. If we know C, it turns out we can get D in a very simple way. D is just the z-score of C. That is, D is just C minus mu over sigma, using the z-score formula. The z-score formula, remember, is z is x minus mu over sigma. That's transforming from the x-axis to the z-axis. People just say from x to z. You take a point on the x-axis, and you find a point over here on the z-axis so that the area to the left of your x point is the same as the area to the left of your z point. And of course, going the other way around is just as straightforward. Take a look at this formula right here, this equation. D is C minus mu over sigma. Now, if you knew the point D over here, you could put that number in here. You'd know mu and sigma, and you could transform back to find the point C. So you can transform between the x-axis and the z-axis in such a way that the area under the normal curve that you have over on the x-axis is the same, that is, to the left of C, is the same as the area to the left of D over on the, under the z curve. All right, let's do an example here. A couple examples. This first one's more or less just a reminder of using the z-score formula. If the random variable x is normally distributed with mean 12 and standard deviation 3.7, mu and sigma, what's the z-score of the x value? 9. Well, I'm just going to use the z-score formula here. Z is x minus mu over sigma. And in this case, the x value I'm looking at is 9, so I'm going to have 9 minus mu, the mean, 12 over sigma, which is 3.7. And this turns out to be, about negative 0.811. All right. The point C on the x-axis, underneath the normal curve with mean 5 and standard deviation 1.3, has z-score minus 2. What is C? Well, even though it's not necessary for the solution, I'm going to draw a picture. I draw pictures for everything like this, and so should you. After the first 100 years or so, you can stop, but up till then, you should be doing it. So this is the standard normal. It's got mean 0, standard deviation 1. Over here, this is the normal curve with mean 5 and standard deviation 1.3. So this is 5, and really I don't care too much about the rest. Okay, so over here somewhere on the x-axis, there's a point C, and I don't really know where it is yet. What I do know is that if I transform it over to the z-axis, its z-score is -2. Over here, I know where -2 is. It's right there. And so I know that the area to the left of -2 under the z-curve has to be the same as the area to the left of c under the x-curve over here, this one right here. To actually find it, to actually find c, I'm just going to use the z-score formula. And I'm going to start with z is x minus mu over sigma. This time, of course, I don't know x. I do know mu and sigma, but I don't know x. Instead, what I know is z, so I'm going to put that in. 2 equals, my x value that I'm looking for is c, so I'll use that. C minus 5 over 1.3, putting in all the stuff I know. And if you just do a little work, you do some arithmetic on this, you would find that this is about, I think it is, C is 2.4. Let me ask you one more of these. The question is, what's the z-score of mu? And I haven't told you any distribution there, right? Just a normal distribution. What's the z-score of the mean? Well, if you have this visualized correctly, which will really only happen after drawing things a lot of times, right? So let's say this is the normal curve with mean mu and standard deviation sigma, and this is the normal curve with mean 0 and standard deviation 1. So this is mu. Okay, I want to know where mu goes under this z-score transformation here. What has to be the case is that the area to the left of mu over here has to be the area to the left of its z-score over here. And the area to the left of mu is just going to be 0.5. Right? Half the area is to the left of the mean under a normal curve. So that has to be true over here too. The area to the left of the z-score of mu has to be 0.5, and so mu has to transform over to 0. The mean over here has to transform to the mean over here. All right. Let's do one of these that requires a little more. Suppose that x is a random variable normally distributed with mean 10 and standard deviation sigma, and that the z-score of the x value 8.7 is -0.95. What's the probability that x is greater than 8.7? All right, you should read these aloud to yourself for a while, by the way. It helps to get the notation and meaning in your head. So let's draw pictures. The x and the z. And here's z, 0, -1, -2, 1, 2. All right. Over here, just some normal curve. What's the mean? The mean is 10. This is the x curve. This is n of 10 comma sigma. I don't know sigma, right? So I don't know what else to put in here, but I know the mean is 10. And I know that I'm looking for the z-score of the x value 8, no, I'm given the z-score of the x value 8.7. 8.7 is going to be out here somewhere, to the left of 10 for sure. And what I want to know is what's the probability, I'm just going to put it somewhere, let's put it there, 8.7. What I'm asked for is the probability that x is greater than 8.7. So I'm looking for this area here to the right of 8.7 underneath this normal curve. If I knew sigma, I could compute that with normal CDF, but I don't. However, I do know that the z-score of 8.7 is -0.95, which should be right about there, and almost -1. And so the area right of 8.7 under this curve has to be the same as the area to the right of -0.95 under the standard normal curve. Okay, that is to say, the probability that x is greater than 8.7 is equal to the probability that z is greater than negative 0.95. And that you can just get on your calculator, right? That's going to be approximately 0.8289. Okay. Sometimes it is necessary when doing things to transform over to the standard normal to do things. You'll see examples of that, really essential examples of it, a little later in the course. All right, here we're supposed to find the area between z equal negative 0.73 and z equal negative 0.94. Well, let's just draw a normal curve. Right, in this case, it's just the z curve. Okay, so the middle is 0. Good enough. All right, what are the 2 points? Negative 0.73, that'd be about, this is negative 1, so it'd be about 3/4 of the way to that. This is negative 0.73. And the other one is negative 0.94, which is almost 2 minus 1, so this is negative 0.94. Okay, so I'm looking for the area over this interval here. That's the area I'm looking for. First of all, it's very tempting when you see something like this to punch minus 0.73 comma minus 0.94 into your calculator in normal CDF, which, if your calculator is like mine, will give you an answer. It'll just be the wrong answer. It'll be the negative of the correct answer, and you can't have negative probabilities or areas. So you got to get those points in the right order. But now, once you've realized this, all you have to do is the usual normal CDF of minus 0.73. There we go, I did it. Normal CDF of minus 0.94 to minus 0.73, and that just turns out to be 0.0591 approximately. Notice that no one had to tell me that this was the standard normal distribution because of the use of the variable z. Right? Here it just says under the normal curve, and when the variable is z and it says something like that, it's the standard normal. All right. One more topic in this section, and that is quantiles for continuous distributions. Really, it's quantiles for the normal distribution. Let me tell you how we get there. Think back to the case of a discrete data set. Right? A discrete data set, that's just a numerical, of course. That's just a bunch of points on a number line. Right? There it is. All right. And how do you define, say, the first quartile Q1 in that case? Well, you start at the left and you keep going until you've passed 25% of the data points. So there's Q1. Similarly, Q2, that would be the median. Right? That'd be 50% of the data points would be to the left of Q2. Well, since this is 25% of the data points, if you put each of these numbers on a slip of paper, identical slip of paper, put them in a sack and shook it and pulled one out, what's the probability that you would pull one out that was less than Q1? The probability would be 25%, right? 1/4, because 1/4 of those slips, they all have the same chance of being drawn out, and 1/4 of them have a number less than Q1. Right? The same thing would hold for Q2. What's the probability you draw one less than Q2? Well, it'd be 1/2, because half the slips would be less than Q2. And it doesn't really matter how many data points you have. Right? If you had 1 trillion data points, that would still be the case. Q1 would be some number, so that 1/4 of them would be less than Q1. And if you pick one of those values at random, the probability you'd get one less than Q1 would be 1/4. So in general, no matter what, the probability, let's say the random variable x is less than Q1, is going to be 0.25. Right? And that's how Q1 is defined. Right? Q1 is the point on the x-axis such that the probability that x is less than Q1 is 0.25. And the same for Q2 and Q3, and same for percentiles, and for that matter for deciles and quintiles and all the other things, most of which we don't use. So if I look at a normal distribution here, let's say this is n of mu and sigma. So here's mu. Where would Q1 be? Well, it would be the point on the axis. I'm going to put it right there. Q1. I don't know what it is. It would be the point on the axis such that the area to the left of it, this area, is 0.25. Because that's what this means in terms of area. The probability that x is less than Q1, given that this x has this normal distribution, the probability x is less than Q1 is 0.25. That's what Q1 is. Similarly, Q2 would have to be the mean, right? Because half the area is to the left of the mean, and so on. Well, how do you compute a thing like this? If we had a number on the axis and we wanted the area to the left of it, we could use normal CDF. But that's not the way to find. Now, here we're given a probability or an area to the left of some number, and we need to find that number. Well, there's a function in the calculator that will give that to you, as it turns out. It's called invnorm. An invnorm, this is for normal distributions. Invnorm takes 3 arguments. You remember that normal CDF can take 2 or 4. The first 2 are always the left and right endpoints of an interval, and the last 2, if you put them in, are the mean and standard deviation. If you don't put them in, they're just 0 and 1. Invnorm can take 1 or 3. For a thing like this, where you have mu and sigma different from 0 and 1, it takes, the first argument it takes is p, and that's the probability that you're given, or area that you're given, same thing. And the second and third are the mean and standard deviation. And what this is the point, I'm going to give it a name, let's call it x0, on the x-axis, or whatever you've chosen to call the axis, such that the probability that x is less than x0 is equal to p. Or, if you prefer, such that the area under the normal curve with mean mu and standard deviation, sigma, to the left of x0 is p. That's the same thing. Oops, I'm sorry, you can't see that. Probability that x is less than some number is the same as the area to the left of that number under the PDF. All right, let's do some examples. First, let's find Q1 under the normal curve with mean 53 and standard deviation 8. So we'll draw a picture as usual. Let's see, this is 53, don't really care much about the rest, n of 53, 8. And we're supposed to find Q1. Q1, remember, is a point on the x-axis here, Q1, such that the area to the left of that point is 0.25. 25% of the area is to the left of Q1. Q1 then has to be invnorm of 0.25, comma, the mean, 53, comma, standard deviation, which is 8. And let's go ahead and put that in. Go ahead and punch it in. This stuff is in the book also. Okay, where is invnorm? It's on the distributions menu. So second vars, and invnorm is right underneath normal CDF. There it is, put it on the screen. And now I'll type in the numbers. Okay, I need 0.25, and then I hit the comma key, 53, comma, 8, and there you go, 47.6041. So it's about 47.6041. Okay. Find the 63rd percentile under the normal curve with the same normal curve, mean 63, standard deviation 1. And so this is 53.8. This time I'm looking for the 63rd percentile, P63. And the thing about P63 is, what defines it is that the area to the left of it under the normal curve is 0.63. Right? So 63% of the area if this might be P63 here, the area to the left of it is 0.63, which means you find P63 with INVNORM of 0.63, and then the mean, and then the standard deviation, so 53.8. If you put that into INVNORM, you'd get something like 55.6548. All right. Here's something that looks like a word problem. The number of beet seeds in a 1 ounce box is normally distributed with mean 1600 and standard deviation 114. What is the 33rd percentile P33? Well, we'll draw a picture here. Right, so the mean, 1600. This is the normal curve for 1600, 114. And we're asked for the 33rd percentile P33. Just like the one before it, P33 is going to be the point over here, so that the area to the left of P33, this area, is 0.33, 33% of the whole, because the whole is 1. So P33 is just INVNORM of 0.33, comma, the mean, comma, the standard deviation, and that turns out to be, about 85.69. Oh no, it doesn't. I looked at the wrong place in my notes. It turns out to be about 1549.85. That makes a lot more sense. All right. Well, I bet you can guess the answer to the next one. Scores on a civil service exam are normally distributed with mean 75 and standard deviation 6.5. All right, let me draw a picture before I even go further, because I know I'm going to do it. So this is the normal curve. We call this axis X. The normal curve with mean 75 and standard deviation 6.5. Okay, what am I asked for? What is the lowest score you can earn and still be in the top 5%? Well, that would be the cutoff for the top 5% here. Right, so this area here would be 0.05. Well, we don't have any function that will tell us a point on the axis when we know the area to the right of that point. But we do have a function, INVNORM, that tells us a point on the axis when we know the area to the left of the point. And if this area up here is 0.05, then this area to the left of this point must be 0.95, right? Because they have to add to 1. So this is, in fact, the 95th percentile, P95, because the area to the left of it is 0.95. So the cutoff score here is just P95. And now you know how to find that. It's INVNORM of 0.95, comma, the mean, comma, the standard deviation. And that's the thing that works out to be about 85.69. So if you have an 85 on this test, you're not in the top 5%, and if you have an 86, you are. All right. Before sowing dragon's teeth, Cadmus, and you can look up Cadmus of Thebes, Cadmus discarded the longest 5% and the shortest 5% he had. If the lengths of the teeth in his collection were normally distributed with mean 24 centimeters and standard deviation 1.9 centimeters, how long were the longest and shortest ones he kept? And we're supposed to round to the nearest hundredth of a centimeter. Okay, so here's a picture. Well, let's see, the mean is 24, so this is 24, comma, 1.9. Nice long teeth. And we'll call this axis X. Okay, he's going to throw away the longest and the shortest 5%. So we want the cutoff for the longest 5%. Right? Just like the previous problem, that's going to be P95, the 95th percentile. Over here, we want the cutoff for the bottom 5%. And that, of course, is P5. Right? That's the definition of P5. Right? The probability X is less than P5, or the area to the left of P5, 0.05. So the shortest would be P5, which would be given by INVNORM of 0.05, comma, mean, comma, standard deviation. And the longest would be given by P95. Hinge norm of 0.95, mean, standard deviation. This one turns out to be about 20.87 to the nearest hundredth, and this one turns out to be about 27.13. So he would throw away any teeth that were shorter than 20.87 centimeters or longer than 27.13 centimeters. All right, that's about it for this section.